Welcome back to the Structural Engineering Podcast. This episode, we learned quite a lot from Trevor Haskett at Motioneering. If you haven't heard that name, they're one of the premier damping system providers and consultants and have projects across the world ranging from the Grand Canyon Overlook to Taipei 101. So please enjoy, and as always, if you have any questions for us or Trevor, feel free to reach out.
So I'm Trevor Haskett. I'm working at a company called Motioneering Incorporated here in Guelph, Ontario, Canada. And we are a sister company, I suppose, to Rowan Williams, Davies and Derwent, or shorter, it's known as RWDI. And RWDI is perhaps most well known internationally over the decades for wind tunnel testing. Lots of the sort of biggest, greatest, tallest structures, bridges and buildings in the world. And this company, sister company that I'm in, Motioneering, we deal with some of those structures are better designed by including a damping system. And that's the team that I work in.
Cool. Well, thank you very much for joining us. I think the questions I want to start with are just a little bit more about Motioneering. What type of dampers do you do? I guess the first one I have here is, what is the first, just where you started, what is the first project from a damper's perspective that you guys worked on, and how did that evolve into your current position?
So the dampers can be really big, or they can be kind of small. And I think probably the one that most people are going to agree that really was our first kind of authentic damper was a project, Park Hyatt Tower in Chicago. And it was a 300-ton TMD. So it's big. Tune mass dampers, 300 tons in mass. And that would have been in just a little before I joined the company. It would have been about 1995 or so, and commissioned in perhaps 1998. And we don't only do the solid heavy steel tuned mass damper types of dampers, though we also do smaller ones. We do liquid based ones for buildings, for bridges, pedestrian floors. So it's really wide ranging.
And are most of the dampers you do tuned mass dampers? Is that the fundamental? I know you have a lot of other types, but is tuned mass the preferred type?
I think that's probably, it's a niche in a way. It's a big niche. I guess it comes from our connection to the wind tunnel. So it's often in the interest of a structural engineer to not just use a code analytical technique to design a really, really big structure, maybe a structure without precedent. So you're going to get it wind tunnel tested. Mm-hmm. It just so happens that a lot of these structures are really slender. And so it seems it's probably not much of an overgeneralization to say that really slender structures kind of are best damped by tuned types of damping systems, whether they be a tuned liquid in cavities or reservoirs, or a tuned mass on springs or pendulum suspensions, as opposed to other types of distributed damping systems that you might see in mechanical systems or constrained layer damping. There are lots of great mechanical approaches to this on things that maybe aren't so big or massive or slender.
We've already kind of started using this word damper. What is a damper, and how does it work in a building?
So let's get everybody maybe start on a common framework here so we can add terms on as we go. Think of a guitar string. And it has a certain length and a certain tension on it, and now hands off, if you just pluck that string, it'll vibrate for a while at a certain frequency. That could be like the span of a bridge, simply supported between abutments. And what that string lacks, the reason it resonates, it vibrates for a while after you've plucked it, is that it doesn't possess a lot of another property that we call damping. So if you were to just gently rest your finger onto that vibrating guitar string now, it mutes it instantly. The vibrations are absorbed by your finger. This is more effective if you touch it in the center where it's vibrating the most, but it also works even if you were to do it pretty close to one of the connection points. So damping really is the means of a vibrating system to have its energy drawn out and dissipated, basically wasted as heat. And so structures of all types that we like to engineer in the built environment, buildings, high rises, they're traditionally designed with a lot of strength, and the strength comes from steel and concrete. They have a lot of mass as a byproduct of that, floors and furniture and occupants. What is not traditionally intentionally designed into them, and it would be really hard to do, is the damping. Once a gust of wind pops some energy into the building, or once the ground shakes in a seismic event, what was the plan on how to dissipate that energy? And really, it hasn't been a plan. It's been a byproduct for most of most of structural design history, I think. And in recent decades, we've started saying, hey, you would never design a car without a suspension. You wouldn't leave out the shock absorbers. The step from wagon to automobile, that's one of the important components of it. And then similarly, we think that efficient design really should include a damping system now. And by doing that, you can address the vibration needs with damping and only the strength needs and serviceability needs with the structural materials.
Okay, I think you just answered the question I was thinking of, actually, but I'll give it a try anyway. So what in our day-to-day life functions as a damper? So just fundamentally, I'm picturing car suspension, there are shocks and then shock absorbers with the dampers. Is that the most fundamental way to think of this?
Yeah, some of your audience may have the experience of having either owned a vehicle that had a blown shock suspension on it or been driving behind one on the road. And if you see a vehicle and it just continues to bounce, so it hits one bump in the road and it just keeps on bouncing, it's probably a blown viscous damper or dash pod shock kind of thing, we call that, not to be confused with the spring. And maybe if you've sat on the bumper of your own car or a tailgate on a truck, if you sit your weight down on it and it settles an inch and then you stand up suddenly, it sort of does one oscillation and then settles out really quickly. Mm-hmm. And that's because of that dash pod in there, the viscous cylinder. I think that's probably the way most people encounter or understand damping most readily.
Yeah. Okay.
Yeah, I think that makes a lot of sense. Would you say that there is some inherent damping already in a building?
Yep. You bet. So a thought experiment, if you had a tall building, and by tall, we are talking like, say 200, maybe 300 meters or taller, right? 80 stories or taller, to sort of use more international units. How many stories is on a building? If thought experiment, if you pulled it to the side and let it go and it vibrates for a while, every oscillation cycle, and they might take 6 or 7 seconds to oscillate once to north and come back to you at the south side again. But every cycle gets slightly smaller and smaller and smaller. And that is due to the very small amount of intrinsic damping that's already in that system. And it would be, I don't think could catalog accurately all of the places that energy is getting to, but it includes some things like even the flexing that you're doing down at the foundation is radiating energy into the soil as you might very much microscopically move that soil around. You've got internal drywall partitions where they join the header at the top of your walls. And you've got, again, they're microscopic. They're 1/16 of an inch perhaps on a very windy day, but you've got these very small movements of rubbing there. So this is a friction. Rubbing would be a place that energy is lost as well. And even just the bolted joints between columns and beams.
With those being so minor, is there an assumption we make about the inherent damping, or is it, especially when you start getting into taller buildings, how's that evaluated?
There is so much scatter. It's really hard to predict, and nobody really is ever on the hook to predict it for modest structures. Once you start getting to 30 and 40 and 50 story buildings, it might govern your solution. Your ability to, your outcome, whether you have more or less damping, could affect how comfortable maybe your occupants are on a windy day. And whether the building had been sort of a very much shear type deformation structure, lots of columns, but not a lot in the way of moment frames, say, or mostly steel or mostly reinforced concrete, or all of these things play a part. And then how they're detailed internally, whatever the structural engineer had in mind, the trades that came in, they bid on the contract to get their work done as fast as they can. There's sometimes questionable quality control in some of the parts inside of the way these things are finished. There's just so much scatter. But what we would know, and this is where it starts to become more relevant to very tall buildings, is that once your building is over 60, 70, 80 stories, you probably don't have very much damping. So we use a concept called critical damping. And on a critically damped structure, it could be like if you walked up to maybe a fence post, a stake in somebody's garden, post, and you let go of it, and it only vibrated sort of once. It went right back to where you grabbed it from. Mm-hmm. It didn't oscillate at all, and it just went right back. The ability to do no oscillation whatsoever, but quite quickly get back to the spot that you pulled it from, we'd say that's critically damped. And as soon as you have less damping than that, you are fractions of critical damping and or percentages of it. And we would say then that a structure that was 70 or 80 stories tall probably only has about 1% or 2% of critical damping. So it only dissipates 1 or 2% of its energy in each oscillation cycle.
Very interesting. I'm really jumping with this question here, but how much of the damping work is in a retrofit phase? And I imagine if it's a retrofit, you can really measure the frequency of the building and the vibrations. You have a much better understanding of that than any calculation with obvious scatter and not knowing what the final product is going to be, quality control, and things like this. Do you get to do retrofit projects, and is it easier in that sense, or is it complicated in much different ways?
I think broadly speaking, you've got a couple of classes of problems. So when we have a really tall high-rise building, retrofit is quite uncommon there. The space has been programmed to the max. There isn't a closet left over. There's no space on the roof, mechanical equipment everywhere, and there probably just isn't room. It's pretty rare to do any sort of retrofit on a high-rise. When it comes to, there are some occupancies like really big ballroom floors, where retrofit is possible, and then it does enjoy the advantages you were just speaking to there, where hey, if this is an existing structure, so on the upside is we know what frequency it is already, so it does simplify the design of what perhaps would need to be a unique customized damping system. We don't have to design so much variability, tunability into the final design in order to make it function well on site.
Yeah. Okay, that makes a lot of sense. Okay, I'm going to stick with my theme of kind of doing out of place questions just for a moment. Could you just expand a little bit on what type of dampers Motioneering has available? So we mentioned mass tune dampers, and that's kind of the big one that we really want to talk about. But you also have liquid-based dampers. Is that the second category, the only other category, or can you break it down a little finer?
I would say that in the tuned type systems, where fundamentally what we have is a large concentration of mass, and it is not obligated to move in lockstep with the structure. So when it's designed properly, this concentrated chunk of mass or location of mass, which could be a pool of sloshing water, it tends to lag behind the motion of the structure. And particularly when the structure resonates at its natural frequency, this mass lags behind by about a quarter of a cycle, and it always does that. Mm-hmm. So those variations on that theme tend to be that sort of very broad niche that we work in. And as it turns out, I think our track record is probably something more like 4 or 5 times as many liquid damper solutions in high-rise buildings as solid mass dampers. Wow. And the reason for that is they are just much more affordable. Yeah. They take up a little more space, but the mass, the material that you have to get to elevation is just water. It can be pumped up there into a properly designed tank for it, as opposed to something with a lot of detailed mechanical design.
Are most of the liquid dampers you have dispersed in a sense? Like I've seen these spaced around the stairway, or is there a floor or an area of a floor high up dedicated to this, and it just happens to be a liquid damper?
All of the above. So that's kind of where we get our groove. So because we aren't selling only one type of solution, we're a consulting company first. That's where our roots are. So should it be identified that the structure either kind of needs a performance improvement and damping is going to be investigated as the way to do it, it's very consultative. Show us your floor plans. We know how much performance improvement we want. We have a sense of what kind of mass, what kind of geometry these systems might take. Could it fit here on the east side beside the stairwell? Could it fit over here? If you could just move some of this building maintenance equipment on the roof, we could probably get enough space up there. So it's sometimes a single tank, sometimes there's 2 or 3 tanks of water. Sometimes there's even a TMD and a sloshing damper in the same building.
Yeah. So kind of going with that theme, you're saying, depending on the design team has determined that one is needed. I couldn't even think of how I would start looking at that. How does that process look like from, maybe the design side before it comes to you? I don't want to allude any more than that, but what does that whole process look like?
So there's a first for every structural engineer to get involved in this business of putting a damping system into the building. So it kind of starts that way. Whereas we often do second, third, and fourth projects over the years with the engineers, and then they come to us in a very different frame of mind. So the first time around, you may not have been expecting this was going to be a problem. Maybe you're building a little taller than ever before, or you're in a windier city than you're accustomed to doing your designs in. And you get the bad news that despite the traditional attempts to change it with mass and stiffness, maybe the architect is less inclined to help you with aerodynamic improvements on the building for aesthetic reasons, or the way the program space has already been laid out. And now you're stuck, and you're going to say, let's try and find a bit of space. A bit of space could be as little, now depending on how big your structure is, a little bit of space could be as small as a 20-foot by 30-foot room, maybe 1.5 stories tall, 2 stories tall, be plenty. And we can start riffing on something like that. So you kind of have to be able to knock together a bit of contiguous space on a floor plan, preferably right near the top or right at that point of the structure that it moves the most. So of course, on a bridge, this would probably be mid-span, and in a great big multi-use banquet hall ballroom floor, this would probably be in the middle of the spans, the big long truss or girders that you've got going across that space. And then it's back and forth. It's consultative. We say it would, maybe we need a little more width here, but we could give you a little bit of length back. There's that. So there's a bunch of give and take. Now, the second or third or fourth time we deal with maybe the same design team, they're probably already coming back to us saying, hey, I remember last time I'm building a building, it was like the last one, or it's taller, and I've already put aside this 40-foot square space for you. We put it aside, and it's because they've already clicked with it's like a paradigm shift for them. They've already understood that, hey, I could have built a 60-story building with all my conventional techniques. I can use the same footprint, and I need, let's say, one more story. Most of it's going to get taken over by this damping system. But the trade-off is I get 9 more stories of saleable space, right? It's a small cost. So all of the additional floors that can be sold or leased out more than cover that encumbrance of some space to put aside for a damping system. It's the enabling technology.
While we're on the subject of tall buildings and the process involved, I want to talk about an enormous part for a second. So something like Taipei 101, how does Motioneering get involved, and what does the request to your team look like? Now, you said they may have an idea. They want a floor taken up by a mass damper, and it's going to be near the top of the building. But what does that look like? Like from a software perspective, they give you the estimated frequency and the amplitude and the wind speed, and you help them get to a mass tuned damper approach. From a process standpoint, what does that look like?
Right. So we're probably having some very detailed engineer-to-engineer conversations around about this point. We've been through some floor plans and what sort of space will become available. Part of the work that the wind tunnel RWDI side of the operation will be handling is what are the wind speeds, what are the responses, and the structural engineer is probably iterating on the structural scheme a little bit. So what we need for the damping system design is the dynamic sort of summary of how the building behaves. So we would call those the natural frequencies and the mode shapes, or the eigenvalues and the eigenvectors. And really, we probably only need the first 3 vibration modes for the wind aspect of this design. And maybe those are still in flux, or maybe they're still floating around a little bit. But we start designing to that frequency, and we have a very detailed understanding of what is the wind climate. So there's a lot of probabilistic work that goes on in the background here. We have a meteorological understanding from airport data from many decades rich of observations of wind data in there. And we will numerically, this is part of the task that we take on, we make engineering approximations of how the structure behaves based on those dynamic properties that the structural engineers has determined and has shared with us. And then we try this version of a damping system, that version, longer columns, shorter columns, sort of the articulating members of the damping system. And we iterate on that internally. And if it makes any macroscopic changes, like it turns out we don't need as much space, say, yeah, that's great news, we can give you a few feet back. Bad news, maybe we need another couple of feet space because the amplitudes are so large. These dampers are usually put in for comfort, for very frequent wind events, monthly, bi-monthly, maybe annual.
Yep.
But they're going to be in the structure when the big wind comes or when the big seismic event comes. So you can be sure that we are also having to design it for the ultimate limit states events, and they will determine how much stroke and how much force has to sort of manifest within all of the myriad connections of the device. But then also we're feeding back to the structural engineer at all of these interface points that it hangs from or is supported from. These are the loads that you've got to be able to resist with your probably reinforced concrete in the area.
Okay. And actually, since you mentioned the high recurrence events, I was curious. So if you have a fluid viscous damper or even if it's a mass tuned damper, if you were to take that out, if someone did not do the proper service on it, is the building
good question.
fundamentally fine, or is the mass tuned damper incorporated into the strength of the building?
Important question, right?
Yeah.
Really, really, really important. The current practice worldwide is not to assume that the damper has been properly maintained or not fallen into disrepair or even sabotaged. The current practice is assume it's only there for serviceability requirements, not for safety, life safety or strength. There will come a day when wind performance, the amount of steel that you're going to see put into a building requires that a set of damping elements is operating correctly. It's inevitable. I see it's fraught with a lot of discussion. This is going to be a peer-reviewed solution. This is going to be put perhaps before code committees. And the watchword here I think would be redundant. It has to be as massively redundant as all of the bolt and column beam connections throughout the building. Traditional construction techniques. So at a minimum, I'd expect that you'd see a solution like this someday have many independent dampers in the structure, smaller, distributed around the top parts of the building. But then should any one of them fall into disrepair or be inoperable or be down for a maintenance or something, we would still say, hey, probabilistically speaking, we can probably count on half of the dampers still working well, and this is then maybe the reduced set of loads that could be designed in the structure. We're not there yet.
To build on that, and this is a really hard question, I would imagine, but do you have any idea of the cost savings to the structure if we were to start designing that route?
No, I don't have a good set. You know what? There's a really good similar question. I'm not sure whether I'm going to answer it satisfactorily. We've been involved over the years in studies to say, look, yeah, okay, we're just meeting serviceability, comfort requirements here, or some of the alternatives are remass the structure this way, size up the beams this way, add some more, trusses this way, or a damping system. And how do these costs compare to each other? And we have been involved in exercises like that a couple of times. It's a lot of extra work for everybody in the project team, so it's not very often we get a chance to do it. And it, it's favorable, but you still have to have your head around the fact that the top of the building is conceptually in everybody's mind, it's already earmarked for the penthouse or the multifunction rooms. Like it's the most expensive real estate in the building. So it always feels like you're taking something away to give room to a damping system, as opposed to, hey, I just got 5 more stories on this thing. Of course, I can turn over half a story to a damping system.
Yeah, and it seems like with Taipei, they did a pretty good job utilizing the damper as a means
display
to get people up there,
yeah,
and to display it too. So it seems like a pretty cool. It could be a pretty cool architectural aspect of a building. Is that done often, or are they hidden pretty frequently?
By and large, they are hidden. There's not much to look at in a sloshing damper, so we'll just put them all to the side for a moment. But the tune mass dampers, we've done a couple that are architecturally pleasing, aesthetically revealed. They're part of the tourist experience. From the lookout observatory levels. We've been involved in some that aren't built yet, or some that aren't going to get built. The Shanghai Financial Center is another great example of a great big 1,000-ton TMD with a beautiful jade sculpture on it that is open for the civilians to come up and view.
Yeah.
And the revenue, it's hard to say that somebody who's paid $40 for an elevator ticket to go up to these observation decks and restaurants and overpriced tourist trinkets and all that sort of stuff, it's hard to say they're there because of the damper. But to some extent, it increased the draw.
Yeah,
right.
We can certainly hope they're there for the damper. That's at least in my head why.
Yeah, well, I'm not gonna value at nothing the view from these types of elevations. That's one of the best parts of my job, is getting to see these views that most people don't.
Yes, certainly.
But the revenue from these observatories is big compared to the cost of that owner putting in a damping system. And more than a few of them have, their eyes have lit up when they do a little bit of math on that.
Yeah. And just while we're talking about the public being able to see a TMD, does it move in a typical windstorm? What sort of movement are we expecting? And can the public see that very clearly? Is it high enough magnitude that is obvious, I guess, hanging down in a room, however this is exposed?
On many occasions, yes.
Yeah.
But you couldn't guarantee it on any given day.
And we were thinking taipei, is it feet of movement, or is it, in my head, TMD is just a few inches back and forth. That is based on nothing, just what I have decided in my head. But yeah, for taipei, it's quite a tall building. Yeah, is that really moving so that an observer can clearly see it?
So putting aside, were you lucky or unlucky having been there when a seismic event might have happened? And there is footage of that, people's handhelds or security camera footage been put onto the internet for, video streaming channels. If you went up on to that level at Taipei 101 on any random day of the summer, you'd probably see it moving some inches.
Yeah.
My own perceptions were changed when I went there for a period of time during the commissioning of that damper, and they have typhoons, we call them hurricanes here. They have typhoons regularly. So twice in my visit there was a typhoon, and in a typhoon, the locals behave like it's no big deal. They go out after the event, they put the trees back in the ground. They're already wired down, so they don't blow very far away. And life goes on again. And during that event, had you been up at the TMD for those two strongest typhoons of the year, which happen every year on average, you would have seen it moving perhaps plus and minus 1.5 feet, 2 feet.
Yeah.
The strongest storm of the decade, the strongest storm of the century, of course, those are incrementally larger, and it could move as, plus or minus 3, 4, 4.5 feet in the sort of getting close to the design level events. But then there would be 6 days out of any 7 days in a week where the amplitude is just inches.
That makes sense.
What about maintenance for those? I understand the fluid, the viscous dampers, maintenance kind of makes sense to me. But what about a mass tune damper?
It's quite similar. So we aren't designing every element of these dampers from scratch. We borrow wherever possible mature technologies from other market segments. So the cables that they hang from, they're from like the mining industry, and the big shock absorbers, they've been used in other industry, manufactured by others, very, very advanced devices. So we've minimized the wear as much as possible, and also by having a meteorological understanding, probabilistic understanding of meteorology there, we can predict in advance how much wear and tear there will be, and that becomes part of the specification for these devices. So with time, you would expect that eventually something like a seal that holds back the pressure in a viscous cylinder, it could need an overhaul. Now, we've been doing it for over 20 years, and that hasn't happened yet. The specifications have been pretty sound, and no parts have worn out on any of our projects. So, but we do advise and we do deliver at the end of the project the handover manual, the maintenance, the inspections, and say, hey, do take a peek at this, and in your 20-year budget renewal, anticipate that maybe you're going to want to overhaul some seals in place someday.
Do you guys perform that work as well, the maintenance of these?
No, I don't think we would. My expectation is that as these devices are procured from other specialist fabricators, they are the ones who would have the tools to open up relatively large pores and hold on to some fluid while they slip a seal around it and put it back together again.
Okay. What sticking on with Taipei 101, what things have we not asked that you think would be really cool for the audience to understand and know about that project?
Well, it is heavy. It's 720 tons, or we're sort of bilingual here. We do 660 metric tons. I used to sort of try to make an approximation that like a Toyota Tacoma pickup truck is close to 2 tons in mass, right? So this is like 350 Toyota Tacoma is all smashed into a great big 6-meter diameter ball, swinging back and forth ponderously.
Is that a steel ball?
It is solid steel. Yeah, and one of the things that's actually quite intricate about it is we've got to design it so that it can be installed.
Yeah,
so,
was it assembled up there and taken in parts?
Yeah, so the maximum crane lift is something that we have to get taken to mind very early. This is a discussion point earlier than maybe others even care to get into the discussion, but whether it's an 8-ton capacity or a 13-ton capacity lift with the crane matters, because all of the parts that we're going to require be assembled up there have to obviously be lifted. And the designs tend to consist of some high strength alloys in the places where you've got loads to carry, and then the rest is sort of dumb steel, lower strength steel. And it's a combination of those things. So some of it would be, it's off. We usually fabricate all of the high strength steel. We see it assembled at a fabricator's shop. It's a great sign off point. It's a handover before it goes to the shipping yard to be staged for the erection process. And that's when we get to see that all the alloys come together well. And then we don't bother adding the ballast until the final install.
Very cool. And I mean, if someone were to ask me to guess the mass of a TMD, as a percentage of the building weight, is there any ballpark that you can estimate and say, if let's just magically 100 kit building, and I know it's nothing, would you assume it is 1% of that about?
Yeah, there's an order of magnitude here that we can home in on. The actual number is going to depend within some limits. The actual amount's going to be based on how much performance improvement the building requires. And so nobody's going to put in more TMD than they really need. That being said, you can do a lot of good work when you have 1, maybe to 1.5% of the modal mass or the generalized mass, this is the mass that's participating in that eigenvector vibration, which for a high-rise building, that tends to be about maybe say a quarter or a third of the building weight. So if we had 2% of a quarter of the building, what are we at there? We're 2% of a quarter of the building. So about 0.5% of the net building weight above grade. With that much mass, you can do a lot of good work. You could totally change how well this damping or the building dissipates energy.
Yeah, that makes sense. How would you describe what a mass-tuned damper is capable of resolving? Now, we think of oscillations, vibrations as the big issue, but is the acceleration, the amplitude, or just the fact that there is a frequency involved and then, the critical damping is not returning to zero quickly enough? So what is bothering people specifically, I guess, and how does the damper help?
There are probably a couple aspects of a vibration that it's resolving. Our earliest systems were all about occupant comfort or the perception of motion, which turns out to be our vestibular systems. We recognize acceleration. So if you were in a closed room, no windows at the top of the building, we got into this originally because a peak acceleration or a persistence of accelerations might be objectionable, and you might even see it. Like you might be able to see if you're standing at the sink. Maybe you don't stand at the sink if you own the penthouse, but if you were washing dishes, you could maybe see the water moving or the water sloshing in the toilet bowl. Sometimes there's reports of doors swinging on hinges in big windstorms. So these are kind of acceleration driven, and it certainly helps with those, shaves them down, by 30 or 40 or maybe even 50%. There, I'd say in recent times are also aspects of the actual displacement that are also benefits are being derived from reducing those peak displacements, because displacements can cause noise, they can cause sound. So the mechanical plumbing risers in the building might be sort of rubbing and chafing on a beam nearby, or the drywall headers could be rubbing and making a sound. We've even seen the electrical wiring inside the walls, the armored conduit, the sort of flexible steel helical looking coil that the regular insulated wires are inside of. The way it's been lashed on to steel joists, not joists in the wall, the studs, zip ties, and then very small strains in the system is causing these armored cable conduits to rub and make terrible noises.
Squeak, yeah.
Yeah, so this is probably more a displacement related issue, or cracking of partitions. In the top of a door frame or something, you might see cracks in the drywall. These are these are strain related as opposed to acceleration related. So it's a bit of each, I would say.
Okay, now going off the topic of the tuned mass damper now into fluid dampers, could you give us a kind of a basic understanding of what that looks like?
Yeah, there are a couple of ways to do this with fluid, and it's almost always water. At least when we're talking about really, really big damping systems, water's really the only economical choice to be your fluid, your working fluid. There was a time when we were favoring a design called a tuned liquid column damper, and it's kind of a U-shaped tube partially filled with water. And now it's not really a U-shape, it's stretched. It's really long from one end horizontally to the other end. And the way you apportion the length of that run, the height of the water in those columns at the end, and your cross-sectional areas of the columns in the horizontal, it has a natural frequency. So we pick that geometry such that it interacts as desired with the natural frequency of the building. And then you also have to get some dissipation in there. You're not putting fluid-filled shock absorbers on it, but you can put other turbulence generating devices in there, like a sluice gate or louver vanes or porous screens. And so it's the same principle in the end. What happens is that bulk of mass oscillates about a quarter of a cycle behind the movement of the building. And in so doing, there is a relative movement. Obviously, if you're standing on that floor watching the height of the water columns moving up and down, you can see that. And what you can also instinctively understand then is that the water is oscillating back and forth through these screens, and it's making turbulence, and that's dissipating energy just as heat. That's one way we do them. And now the shortcoming with those ones is that they're uniaxial. So sometimes a building needs to have its north-south response improved, and also perhaps to some extent its east-west response improved. In the last 15 years, I think we've sort of made a bit of a move to a different version of the liquid-filled damper, which is known as a tuned sloshing damper, or there are variations on that name as well. And it's got more of a free surface in the water. So it's a tank, it's partially filled. It might be, it's probably something like rectangular. And you would see the free surface sloshing. Now it's kind of like there's some great video, alarming video, not great if it's your apartment, but there's some video of bathtubs or small pools even in earthquakes or in wind events available to see on the internet, where the water is sloshing back and forth due to wind or seismic excitation and splashing all over the place. Of course, we designed the tanks, they have to have enough wall on them, enough freeboard clearance up to the ceiling that you're not slapping the ceiling with your waves. So it's all self-contained. But again, it's just a question of geometry. How big do you make the tank? How do you put flow retarding resisting devices into it to dissipate just the right amount of energy? Because again, you can't put too much and you can't put too little. So we do a lot of scale model testing to dial this in.
Wow, that's neat. I've heard in the past that there's requirements for water tanks at every so often levels and skyscrapers for fire suppression. Are you utilizing those for this system?
Yeah, in some cases, yes, you're right. And that sort of synergy is in certain jurisdictions easier to come by than others. So in China, for example, they had a nasty couple of tower fires in a short span of time, and they said, all right, from here on out, any building over, it might have been 200 meters or 300 meters, shall have rooftop fire suppression water, gravity drained, to fight fires. No more of this putting compressors down at grade and hopefully the electricity doesn't go out. Right. So if you already have an obligation to have 25,000 gallons or 30,000 gallons of firefighting water on premise at the top of the building, why not make that the right shaped tank? So we can certainly work with the MEP. Now we have some constraints, right? So the liquid's got to be a certain depth in that tank, and it's got to have certain sort of obstacles inside the tank to work as a damper effectively. And as long as the mechanical, electrical, plumbing participants understand that we need to maintain that depth, within an inch or so most of the time, then we can certainly make dual purpose. And this is also true of potable water storage if that's the way that building or that jurisdiction wants to work.
Would there ever, I couldn't imagine, but I just want to ask the question, if let's say they added that up to the roof or they had all these tanks, but they weren't tuned correctly, there wouldn't be any bad side effect to having those in the building, would there?
Not ordinarily, I think. So the traditional wooden slat tanks you see, in Spider-Man movies. He's perched on one of these things on a roof, right? They don't have the right size dissipation devices inside them. They're not filled to the right depth. They're probably not interacting dynamically very much with the building motion at all. And even if they happened to just sort of luck out and pick the right tank geometry for the building with the right natural frequency, it's not going to work well as a damper, probably because it doesn't have the right amount of internal energy dissipation. Now, this is actually a concern, though, for people who are intentionally putting pools up in luxury apartments or rooftop amenity spaces. And we kind of do an anti-tune sloshing damper study for some clients who say, look, this is my pool, this is the geometry of it, and it's going to be oriented north-south, and it's going to be 10 yards long and 3 feet deep, and is it going to splash around a lot? And what would I do about that if it did? Now, it probably, we sometimes get the question, could it also, by the way, function as effectively as a damper? And the answer to that, again, is usually no, because your swimmers don't want a whole bunch of obstacles in the tank with them, right? That doesn't make a good pool. It makes a great playground, but
yeah, it makes a lot of sense.
So yeah, I think it makes sense. Kind of what we talked about before is like the maintenance and that it's a serviceability item, not a strength item. Evaporation and usage, right, of that fluid without being refilled and things. I'm guessing there's sensors, maybe. Well, probably for fire reasons that needs to be filled no matter what. But that's really interesting.
So, we've talked about high rises a bunch, but I know this isn't just about high rises, and you guys have done some really cool systems on bridges. What structures or typical building problems should make us consider a damper? So, when should a standard engineer start to think of this as an option?
You probably couldn't go wrong if at any serviceability criterion for your structure, you ask the question, can damping make this better? And again, bridges turn that problem on its side, kind of literally. And in a bridge, we don't want to, it can be hard to get to these things. There's a bit of a difference. Let me back up a little. A building could be developed. It could be a build and maintain kind of owner who wants to maintain a great property. It could be developed with the intention of selling within 10 years. And it could be resold every 10 years, this property. Who knows what the future of this thing's going to be. And our concern would be 40 years from now, does the condo owners board in this high rise understand that they can't just go stacking boxes in all the corners of this room, where the TMD has to swing, or they can't drain this tank out and fill it with some other thing, or leave it empty, because that would compromise the safety on which the building would have been constructed. So we don't do it for safety in a building for those reasons. The bridges, we'd say maybe suspect, are a little bit better controlled. They're often owned by great big governmental bodies who have proper inspection protocols. They understand their maintenance. They understand their budgets to keep the infrastructure open and operating correctly. Even still, putting in dampers for load resistance isn't popular. Right. So more often, there may be aerodynamic modifications required to avoid galloping, flutter, the sorts of instabilities that could take a bridge down, as some old video has popularized. But if comfort is the issue, then absolutely. So on pedestrians on a long narrow bridge have that phenomenon where they might kind of feed back with the system, and you get into this lateral oscillation like happened on Millennium Bridge in its opening week. Or even you could have a pedestrian lane on the outside of a vehicular bridge, and there's a comfort criteria that applies to them. It's not a question of an extremely strong wind making it uncomfortable for them. There are some lower wind speeds where bridges can behave in very particular self-limiting ways. It's not a structural safety concern, but it might be uncomfortable. I would absolutely go after that with a damper as one of the alternatives to be investigated.
Makes sense. So maybe a more low-level issue, but a more typical issue for a lot of engineers. They would hear of a shaky floor. I remember being called to a project when I was first year or two, and someone was asking, we have a very shaky floor here. What can we do? And I think this really, I think it would still be a very challenging problem for me, but should we think about a TMDs for floor vibrations at all? And is that a system that we can somehow use or connect with you or company and figure out a solution there that can reduce vibrations?
Yep. And this could be done either premeditated when you're designing a new facility, or probably can be accommodated as retrofit if you've got an existing problem. It can be tricky. It is a little bit nuanced. We've seen sometimes where an office space maybe is resold above a grocery store, and the new occupant is a health club. And in this health club, not just the random dropping of weights or people moving around, but if you've got a nice floor mirrored room that you have an aerobics class, it's the synchronized movement of a lot of people, especially almost always musically synchronized, that people can move to. That'll cause real problems where maybe you didn't have it before. And that is a great place to try to go after even a retrofit improvement to a rhythmic excitation. And Stadia would be also another example of that, where you have these massive European football crowds where they're doing their favorite chant for their home team, and you see the stadia just vibrating, a lot visibly in the camera's eye. And this is something that could be improved with dampers for rhythmic excitation as well.
So speaking of a stadium vibrating, what do you think was the smallest project you've been involved with and where it can feel helpful?
The smallest project. I think the lightest tune mass dampers we've ever installed were probably for, a bridge connecting two buildings, sort of like maybe a parking garage to a hotel or something like that, where the mass of the damper would only have to be on the order of 2 or 3 or maybe 400 or 500 pounds, located in the right spot in that enclosed walkway below the floor, or maybe in the ceiling space. I think those are probably the smallest ones that come to mind. There's another class, maybe, this might be worth pointing out as well. There's another class of problem where you've got an architectural feature, and they are, gotta make sure I don't offend anybody in our audience here. They're the biggest pain, because the architectural features are, they're just supposed to look nice. You're certainly not going to alter their shape any. They've been already conceptualized in the overall scheme. They're often very lightweight. They're a minimal frame clad with some sort of beautiful skin on them, and they're lightweight. The wind pushes them all over the place, and they never were anticipated to require a lot of budget. And yet the amount of effort it can take to resolve a vibration problem in architectural features, it can be all out of step with how much money you thought it should have cost. Now, it's usually not a comfort issue. You don't have people riding or traversing these architectural features, but it can be a fatigue problem. So give it long enough and you'll start having bolts shear or panels falling off, and that's a real problem.
Yeah. But yeah, that makes a lot of sense. I think I've seen that kind of before now, thinking about it. So thinking about our audience, we're usually fairly young in their career. Is there any sort of resources you'd suggest they look at, or if they want to start figuring out if their buildings, like you said, the first time engineer starting off implementing one of these systems, where would you direct them towards to even get started?
This is a tricky question. I would say, depending on the type of structure we're in, we maybe have different classes of answer here. If they're in a small team that's getting involved in a very large structure, I think there's probably no good substitute for just getting on the phone with us for a bit of conversation. We can be, because it can be tailored very specifically to what the demands are going to be on that structure. And there are lots of good ways to start and lots of ways that aren't going to get as good traction. I think what's going to be a bit more of a hard to pin down answer would be in all kinds of flooring systems. There are some guidelines on how to design your floors so that you don't have too much vibration. And a lot of young structural engineers will go this one alone, and they'll follow these guidelines. And if my fundamental frequency of the floor is above some threshold, it's probably going to be okay. And it's like any business risk, really. You can spend a lot more time getting down into the weeds and trying to figure out with more and more advanced modeling. Maybe it's a hallway in a hospital that turns out to be, highly trafficked. This would be a bad room to put, or a bad hallway to have a room with X-ray or MRI equipment or sensitive stuff that can be disturbed by really, really small floor motions. So there are a number of places you could trip up on this. Whether you go seeking external help or whether you just want to, whether you've got the appetite and the time and the budget to go digging down into it yourself, I think there's just really no general answer to that one.
I did want to ask real quick, what have we not asked about damping that you think is worth knowing for the general public? Or maybe even, what is the most common question you get from, either a non-engineer or an engineer, whatever, but that they want to learn a little bit more about damping? What is the most common question they have for you?
I think the questions are usually quite technical in nature. At least in my experience, we're normally dealing with there's a real project in focus. People are spending some time and they're under some deadline pressure to get things done. So the sorts of questions that are most common are, how small a room or how much space is this thing going to take? What are the cost trade-offs if I wanted to consider one type of system against another? And this is sort of engineer to engineer dialogue. I think I'm having a hard time coming up with any sort of fun, interesting questions and answers that surprise people.
That's fair. I think and obviously I do not know anything about this, but the only question I've ever gotten, we're looking at a Taipei 101 picture, and someone asked me the question I already asked you before is, wow, how big do you think that is? Because, it looks massive in the photo. So I have no idea. I don't even know where to guess. But now I do.
Yeah, there are some extremely interesting little factoids about a bunch of dampers. So, Taipei 101, it's about 6 meters, a little over, maybe close to 7 yards in diameter. It has, if you look at it, it has the appearance of 4 cables coming up beside each other in each of the 4 corners. And each of those cables is comprised of nearly 2,000 strands of wire. So there are lots of really interesting little factoids about these things that just boggle the mind. And you're glad that there's other people doing diligence on them.
I think that's everything we got, Trevor. So thank you so much for joining us here on the podcast and sharing all your knowledge.
No problem at all. It's delightful. Nice talking with you guys.
Nice talking to you. Thank you.